Hi, calculus students. So this next section is right after the curve sketching. This is on page 34. So 34 in your packet. I want you to start off by reading these first paragraphs. I'm not going to read it out loud, so please pause me and read these, or else you won't know what I'm talking about. Okay, welcome back from pausing. So optimization is sort of like what it sounds like. Optimization means you're finding the optimal value of something. And they give you a few examples of what this means or what this might look like in real life. So like finding a route which will minimize the time it takes to school. We're minimizing the time it takes. That is optimal. We're optimizing this because you're wasting less time. Or finding out how much you should charge for a CD in order to make as much money as possible. Okay, so you want to find the maximum cost that will make you the most money. If you make this CD cost $100, no one's going to buy it. You won't make much money. But if you only make it worth $1, you still might not make much money. So finding the optimum price here. And we're going to use strategies that we've already learned. So we're trying to find the maximum or minimum of some quantity. Okay, so we're finding the maximum and min, but in real life situations like this. So instead of just being given an equation, f of x, we're going to be given a situation where we have to find the equation and then find out how to maximize or minimize that. Down here are the steps for solving optimization problems. Again, I want you to pause me and read through these on your own so you can read at your own pace. So hit pause. Okay. I want to highlight now some of the most important things in these steps. So the first part, step 1, says assign to all given quantities and quantities to be determined. So we're going to assign variables. This is the important part here. So make sure you have a variable for anything that seems important that you might have to deal with. Number 2 is optional. I'm going to skip that one. Number 3 is write a primary equation. So we always need a primary equation of whatever it is in particular that you're maximizing or minimizing. So for this one, area of a rectangle, maybe you want to find the maximum area given certain dimensions. Or you want to, like we said before, minimize the distance so that it takes the less time to get to school. Step 4, sometimes we have more than one variable. For instance, if we're finding area, we have length and width. So if we have more than one variable in our equation, sometimes we have to write a secondary equation. And so we'll kind of deal like this as a system of equations. When we have more than one variable, we need more than one equation to make it, to combine those two to simplify it to be one variable. After this is all set up here, okay? So up here, this is all just set up. It's you understanding what the problem is asking of you. After you've got everything set up, that's when you start doing calculus. Now we're doing calculus. So in order to take the maximum and minimum, this is just like what we talked about in class. You'll take the derivative and set it equal to 0. Important things here that it says is that if you get more than one answer, you can make a sign chart to determine whether it represents a max or min. So that's exactly what we talked about in class, making sign charts to figure out whether it's a max or a min, like that. Okay, and then you also need to pay attention whether the value makes sense. So make sure it makes sense. You can't have negative time, or you can't have a maximum amount of rope that is more than the actual amount of rope you're given. The rest of these, they already bolded this. Be sure that you answer the actual question. If you're given, you have to find a max or a min on a closed interval. Remember to test the endpoints, because max or min can happen at an endpoint, which might not be a critical point necessarily. And then you can verify your answers using your calculator. So you could always graph the original equation and then calculate, use second calculate to find the max or the mins. Okay, we're going to jump right into some examples. So flip the page. Okay. So example 1 says find two numbers that add up to 40. Or two numbers add up to 40. We need to find the numbers that maximize their product. So this table, this is like how we would find trends. If we found two numbers that add up to 40, we could say 1 and 39. The product of 1 and 39 is 39. We could say 2 and 38. The product of those two things is 76. 3, 37. The product of those two things is 111. So we're kind of seeing a trend. The closer that our numbers get together, the bigger our product is, and we want to maximize this. So I could do something like 19 and 21. That product is 399. And some of you are maybe already guessing, oh, it should be 20 and 20. That product gives us 400. So that's what I think is going to maximize it. It took a little bit of guess and check. I think this is the maximum, the numbers that will give me the maximum product, but let's prove it using calculus. So my primary equation that I'm going to have, it's got to be the numbers that maximize the product. Well, oops, sorry, before I do this, let's say what my variables are going to be. So I need to assign my variables. I'm just going to call this S. It's a little bit dangerous naming variables S. Like, it's not normally something I would do, but since it's smaller, I don't know, it seems so convenient. So I'm going to, but just be really careful that your S's don't look like 5s. So I drew this really S-like, so it doesn't look like a 5. And then I'll make this one L, and then P for product. So S, L, and P. And the equation that's used to maximize this, I'm trying to maximize my product. That's what I'm trying to maximize. So I need to make an equation that relates these two other variables that equals the product. So I'm going to do S times L. Hey, it's okay. I'm not talking. I'm just making a video, but you're fine. So this is P equals S times L. That's my primary equation. Obviously, I have two variables in here. I want to reduce that down to one variable. So I'm going to make a secondary equation that relates my two other variables. That's why they gave us this information. That's going to help us write our secondary equation. So since they add up to 40, I can say S plus L equals 40. Now I can use this secondary equation to narrow this down to one variable. I'll solve for S here. S equals 40 minus L. And I'll substitute it into my primary equation. So now I have this equals 40 minus L times L equals 40L minus L squared. Okay, so I've simplified my P. Now that I have an equation, I can find a maximum or minimum. I'm going to start my calculus. So I'm going to take the derivative and set it equal to 0. So P prime is equal to 40 minus 2L. I'll set it equal to 0 and solve for L. So 40 equals 2L, L equals 20. So we were right. Solve for S by plugging in L. So 40 minus 20 equals 20. So these two numbers, 20 and 20, are going to maximize the product. Okay? Let's look at example 2. Example 2 is pretty similar. Maybe you could even pause me, try it on your own. I'm gonna skip this part because to me, I don't know, it just seems like extra work. I'm just gonna do it the way, I don't wanna do guess and check. I wanna know exactly what the answer is, so I'm just gonna start doing calculus. So it says, a rectangle has a perimeter of 71 feet, okay? What length and width would it have so that its area is maximum? What is the maximum area? Okay, so we're trying to maximize area. Assign my variables. Width will be W, length will be L, area will be A. So since I'm maximizing area, that's my primary equation. Area equals width times length. I have two variables, so I need to come up with a secondary equation to bring this down to 1. So I can use this first sentence to help me build my secondary equation. A rectangle has a perimeter of 71 feet. So the perimeter I know is equal to 2L plus 2W. So my perimeter is 71 equals 2L plus 2W. I'll solve for I'll solve for L. So 71 minus 2W equals 2L, which means that L equals 35.5 minus W, divided both sides by 2. So now I'm going to plug this in to finish my system of equations. So the area will equal W times 35.5 minus W. Now I just have one variable. So A equals 35.5 W minus W squared. Alright, I found my equation. Now I'm going to start calculus. I want to find the maximum for this. So I have, I'm going to find A prime. That's 35.5 minus 2W. Set it equal to 0. 35.5 equals 2W. W equals 17.75. Here's my W. And now I can find my length by plugging in 17.75 into my equation for my length. So length equals 35.5 minus 17.75, which equals 17.75. So it turns out whenever we have a square or a rectangle, it can be maximized when you make it a square. So maximum area occurs whenever you have a square, because that happened here and it happened down here. Very similar problems. If you want to try practice 3, go for it. The answer that you should get is, the answer in the end is that the first number is equal, this is the same thing. They both equal square root of 288. Cool, because it's a square. That makes sense. So the two numbers that multiply to equal 288 are square root of 288 and square root of 288. Cool. Okay, but you can prove this using calculus if you want to try. This next one, we're getting into a little bit more complicated word problems. Here it says, an open box is to be made from a piece of metal 16 by 30 inches by cutting out squares of equal size from the corners and bending up the sides. So basically we're going to cut these things out and then bend them up. So X will represent, when we bend it up, it will represent the height. So I'm going to write that right now. X equals height. So when we bend them up, that's how high it will be. What size square should be cut out to create a box with greatest volume? Greatest volume, that means we're maximizing volume. Oh, and then what is the actual maximized volume as well. So we need to figure out the size of the square and then what the max volume is. So here, my primary equation, since I'm maximizing volume, is going to be length times width times height. And using this information, we can come up with our secondary equations. We know that height is x, so let's try to find length and width in terms of x. If we know that this whole side is 30 inches, then if we say this is the length, we can say the length equals 30 minus 2x. And if we say this is the width, then the width equals 16 minus 2x, because we're cutting these two x's out of it. So I had two secondary equations. And when I plug everything in, I'll have the volume only in terms of x. There we go. Okay, and at this point we do have to multiply everything out. I won't make you watch me do that. I'll just say here, when we multiply everything out, the volume equals, what does it equal? 4x cubed minus 92x squared plus 480x. I did it for you. Okay. I have my equation. Now we do calculus. So I'm going to take the derivative and set it equal to 0. The derivative is 12x squared minus 184x plus 480 equals 0. This isn't something that we can factor. So the way I would solve this, and I think I already have it in my calculator, is I graphed that equation in my calculator, graph, and you can see the graph goes through the x-axis twice, so I want to figure out what those two x values are. Since I can't factor it, you can figure out the zeros on your calculator by using second calc, 0, and then finding a left bound, a right bound, and then a guess. Okay, so here's one of the zeros, is x equals 3 1/3. And I can calculate the other one, hitting second, calculate 0. And, okay, I need a left bound and a right bound, and then a guess. Oh, what the heck. Okay, left bound, right bound, and a guess. I don't know why this is happening. But I did this earlier and we got x equals 12. Please believe me. So it's x equals 12. We have two x values and they both can't maximize them. So we could figure out which one would actually give us the greatest volume by plugging them in to my volume equation right here. I could plug them both in. But if we think about this conceptually, if I had x equals 12 and I cut out 12 inches here and 12 inches here, this whole length is only 16 inches. I can't cut out 12 inches twice, that'd be too much. So this one is actually not possible. It just doesn't work in the problem. So this x is the value that we want. Okay, so it says what square size should be cut out. A square size that has these x values. And then we could calculate what is the maximum volume. We would plug 3 1/3 into my volume equation right here. And if you were to do that, I did that using my calc, it's 725.926. Awesome. I'm going to just choose one more to do. I think, sorry, I want to do the best one for you. There's so many cylinder problems. I'll do this example 7, is the cylinder problem. So a 6-ounce can of Frisky cat food contains a volume of approximately 14.5 cubic inches. How should the can be constructed so that the material made to make the can is minimized? So we want to minimize the material. And this problem kind of helped us out. This wouldn't usually be given to you on the test, but if we're trying to minimize the material made, basically the material that makes up the can is going to be the surface area. So our primary equation is this surface area equation. And it tells us that it contains a volume of approximately 14.5 cubic inches. So this is what helps us out with our secondary equation. Because now we know that the volume, which is this equation, is 14.5 will equal pi r squared times h. And we can use this to only write our surface area equation in terms of r. Okay. I'll solve my secondary equation because we can see that there's r and h, and I can't have two variables. So I'll use my secondary equation. I'm going to solve this one in terms of h. I think it'll be easier because there's only one h here, and there's two r's. So I'm just going to solve for h. So h is going to equal 14.5 over pi r squared. A little messy, but it'll work out okay. So I'll plug this h into my surface area equation, and I'll get s equals 2 pi r times, plug in h, plus 2 pi r squared. Let's simplify. S equals 2 times 14.5 is 29. The pi's cancel out, and then one of my r's canceled out. So I just have one r left in the denominator. Plus 2 pi r squared. There we go. I have an equation for the surface area in terms of one variable. I can do calculus now. So let's take the derivative and set it equal to 0. The derivative of 29 over r, this is one that I've memorized. You can also use the product rule or the power rule, but I recommend memorizing anything that's just over the variable. And then the derivative of this is 4 pi r. Set it equal to 0. I'll add 29 over r squared to both sides, and I get 4 pi r equals 29 over r squared. Okay. Multiply by r squared. I get 4 pi r cubed equals 29. R cubed equals 29 over 4 pi. And at this point, I would just plug this into my calculator. When you do that, you get r equals 1.321. Okay? So we know the radius that the can should have is 1.321, but we also need to know what the height is going to be, because this surface area equation uses the height. So here's my radius. I'll plug it into my height equation. So the height is going to be 14.5 over pi times r, which is 1.321 squared. Plug this into your calculator. You get h equals 2.643. Voila. Okay. Per usual, I recommend trying these other two. This one's a little bit challenging. If you want to ask me questions about it in class, I can totally help you out. But here's the work that I did for those. So if you want to copy these down, you can copy that work. Hit pause now if you want to copy this, because I am going. Have a good night.